I'm Tyler Akidau. I am a staff software engineer at Google. I'm also a committer on Apache Beam. This is the evolution of massive scale data processing. It's ostensibly sort of a stroll through history of various data processing systems, primarily focused on interesting aspects related to streaming. Note that even though it says massive scale data processing, it's really the specific set of data processing that's kind of related to these tools. Like, I'm not going into the SQL arena or anything like that. There's a lot of interesting stuff in there that there's just no time to cover. Deep down, this is really a pitch for Apache Beam and why it's cool. We'll kind of get to that at the end, but along the way, you can kind of pretend that it's just a history lesson or whatever and ignore the fact that I'm trying to tell you that Apache Beam is cool. So, we're basically going to look at 9 different systems, frameworks, and have a little bit of conclusion at the end. It's about half Google, half other stuff. And along the way, we'll kind of frame everything within this timeline. So this roughly shows you when each of these projects I'm going to talk about began, and later on there'll be bits showing you sort of interesting points in time, stuff like that. And there'll be lots of pretty colors because that's fun. If you're curious about streaming, 2 articles I wrote for O'Reilly, Streaming 101 and 102, highly recommended. They'll go in much more detail than I will about stuff in here. I stay pretty high level in this talk. Also, unfortunately, because of the ordering, you already missed these if you didn't go yesterday, but Slava Cherniak and Ken Knowles here sitting in the front gave 2 fantastic talks on watermarks and triggers, and there's links to their slides. I think the slides for Slava's might actually be the London ones, so I got to get an updated link from him, but the London ones are great too. But anyway, those are great talks. We'll try to get the videos up sometime too. So let's get started. MapReduce. So all of this sort of kicked off with MapReduce back in like 2003. So what happened then was, folks at Google were building all these systems for doing web crawling, lots of other types of data processing, index building, and they kept building these bespoke systems, and eventually they kind of started to realize 3 things. Like, data processing is hard in general to begin with. When you're trying to do it at massive scale, it's even harder. And when you're trying to do it in a fault-tolerant way on top of commodity hardware, it's even harder yet. And so they kind of got tired of trying to build all of these facets into the systems that they kept rebuilding. And so they came to the conclusion, well, if we could build a framework that will take care of the lower 2 parts, then the top part's probably going to be easier. And thus was begat MapReduce. They published a paper on it a year or 2 later. Many of you have probably read it. I'm sure most of you are familiar with MapReduce. I mean, the basic idea, though, was you would decompose the idea of doing data processing into 2 or 3, depending on how you count, phases. So you start out with this massive data set. You'd have this mapping phase that will translate elements into something else potentially and then key them. You have this shuffle phase, which in MapReduce basically sorted the data. And by virtue of sorting, then grouped everything by a key. And then you'd have this reduce phase where you would walk over all the elements for a given key and do some sort of combining grouping on top of them. And voila, you would produce interesting results. And under the covers, the framework would take care of all of the scalability, the fault tolerance, managing running this on multiple machines. So this was a really big deal for Google, which is why they wrote the paper. Timeline-wise, so the C++ version of MapReduce appeared first in 2003. Python and Java happened not too much longer. The OSDI paper came out in 2004, I think. And then everything else on here I guess Go came later too, so there's another API thing. Most everything else on here kind of relates to, down at the bottom I have a couple of sort benchmarks. Really the interesting progression of MapReduce from the point it was conceived up until essentially present day was just an enormous amount of engineering going into scalability and performance. You can see this, I only have 2 of the points on here, and Marian Dvorsky wrote a really interesting article on our big data blog. You can search for talking about the sort of scalability and sorting and benchmarking that we've done over time. But these are 2 of interesting ones. You can see, like, what are the dates? I can't see from here. 2008, petabyte sort in 6 hours, and then like 4 years later, petabyte sort in 30 minutes. Like, MapReduce just continually was evolving to be more scalable and more performant. And like reduced subsharding, multi-shard combining, shuffle checkpointing, these are all kinds of things that were done along the way. Reduced subsharding was actually like a precursor to liquid sharding, which we'll talk about later in the cloud data flow section, so I won't go into too much detail here. But the main takeaways I want you to get from MapReduce, as far as what I'm trying to get across in this talk at least, were this idea of scalability, but also bundled with simplicity. So you've got this easy framework. You focus on your data processing task, and the system does all the rest for you. So next up, Hadoop. So Hadoop, I'm going to not do Hadoop anything resembling justice, but Hadoop came around in 2004. It really was born out of the ideas of the MapReduce paper, and this basically thinking, well, these are cool ideas, and there's no way for us to use them because you gave us a paper, you didn't give us any code. And so some folks essentially built sort of open source versions of Google File System and MapReduce, which is HDFS and MR. They were trying to build this web crawler called Nutch, which they eventually moved on to Hadoop. Yahoo kind of ended up taking that on. It became an Apache project, and I'm sure all the rest of you know more of the history than I do. Again, I threw up some of the sort benchmarks on here, but in a similar way, things just kept getting better over time. And then, so to really round out my unsatisfying summary of Hadoop, the one thing I want you to take away from Hadoop in this, and this is a vast understatement of Hadoop's impact within the industry, as I'm sure you're all aware, but the thing that's really interesting from the perspective of this talk was that they took these cool ideas that Google had said, hey, look, we're doing this is really cool, and they built an open source ecosystem around it. They went and said, yeah, we'd love everybody to be able to do this, and hey, let's all work together to make this better, which, as I'm sure you're all aware, because that's why we're all here, that just really amplified the impact of this and really resulted in a much better world for everybody else. So I'm going to move on. Next system I'm going to talk about is Flume. So this is Google Flume, not Apache Flume. And Flume was founded in mid to late 2007, basically right when the Seattle Google office opened. And it was founded, there were basically three motivations for the creation of Flume, and I animated those for some reason and then confused myself. The first one was, MapReduce was great, and it gave you this simple framework for writing data processing pipelines, but it was also very limiting. Like the steps you had were map, shuffle, reduce, that was it. If you wanted to do anything else or anything that was more complicated, which many problems are, then you had to write another MapReduce, or write a bunch of MapReduces and somehow run them in the right order. So that was complicated. On top of it, since this was what a lot of folks wanted to do, they ended up writing bespoke orchestration tools for running different MapReduces, sort of sequencing these flows of MapReduces. And also, because MapReduce has this somewhat confining map, shuffle, reduce paradigm in it, they ended up, in order to make things work optimally, instead of writing their code in a clear way that really basically stated what they wanted to happen, they had to start doing hand optimizations. So things like lifting portions of a stage that logically follows a preceding stage up into the stage that came before it, so that things would run faster, stuff like that. And so it really hurt sort of code readability and maintainability. They were sacrificing all this in turn to gain performance. And so the idea with Flume was, well, let's build an API that lets you write pipelines natively. This has a notion of pipelines, and is really built around two main concepts. One is p-collections, which is this idea of a massive data set. And then the second is p-transforms, which are really just transformations of data sets. So you take a p-collection, you transform it into a new p-collection. You can filter it, you can map it, you can do reductions, things like that. And so all of this essentially composed a pipeline. And so you'd write code that looks something like this, and that should be a very familiar thing to everybody here, I'm sure. And so you'd write your code, which is represented by those colored bars on the left. It'd run through this optimizer, which is very much like the optimizers that say databases have used forever. And it would generate a physical execution plan, and it could do smart things to optimize your pipeline that would get it very close to or better than what hand optimized MapReduces were doing. And then it would execute it as a sequence of MapReduces for you. To give you a few brief examples of some optimizations, so fusion is one big win. So like, let's say you have two logical stages in your pipeline. A lot of times people would write these as two logical MapReduces, and you'd have all the time associated with running one MapReduce, then running another after it. In a lot of cases, you can actually fuse these together, and Flume will do this automatically. So consumer-producer fusion, a stage after a stage, there's no shuffle in there. They can be run in the same process. Similarly, sibling fusion, if you've got two stages consuming the same input, and they're in the same process, you can actually run them in the same process, whereas they might logically be written as two separate things. A much more interesting type of optimization would be combiner lifting. So if you have an operation like a summation, which is commutative and associative, oftentimes that will happen after a group by key. So you're saying, well, maybe I'm counting the number of visits per user agent string. How many people do I get from Chrome? How many do I get from Safari? So you have to group all these data together, and then you have to sum them up. And when you're using, especially in a case like user agent string where you've only got, maybe 20 of those or 10 or something, you're gonna end up with really large amounts of data after you've grouped it. But what you can do is you can actually lift part of that summation up into the previous stage. So maybe you're doing some sort of mapping in stage A. Before you group, if you have a bunch of keys for Safari, say, you can go ahead and sum those up and send the partial sum down. And then downstream, you can combine those partial sums. So not only does this reduce network bandwidth, it also spreads out your computation for these potentially hot keys. So these sorts of optimizations were the things that folks were writing into their code and obfuscating the logic of their code in order to gain performance. And with Flume, this all can happen under the covers, which is really cool. So 2010, I think it was, they published a paper on it. It covers the Java version, basically covers the core concepts and talked about how MapReduces were orchestrated and showed benchmarks of comparing clear Flume pipelines versus hand-optimized MapReduces and showed how they got close or better in almost all cases. Again, was founded mid-2007 when Seattle was opened. Was originally, the first project was actually this thing called Lumberjack, which was a custom language for high-level data processing, so sort of in the like pig vein, but they really decided that a custom language wasn't what folks wanted. Folks wanted to use a standard language, and so that's how Flume Java came about. It became rapidly very popular, and so Lumberjack was scrapped. Flume C++ came out a little later. About, what is that, somewhere in 2012, Flume was added to nuclear training at Google, so that means at that point in time, every new person joining Google was trained on using Flume. And that was really the beginning of the end for MapReduce, because at that point, everybody was learning about Flume, and so the usage of MapReduce began to decline at that point. 2013 was when we first launched version 2 of Flume, which no longer used MapReduce as a backend. It uses its own custom backend for orchestration called DAX. And then also, well, actually, I think that was 2013. Yeah, late 2013, we launched Streaming Flume, which was really sort of the precursor to Apache Beam. I'll talk more about that later. So main takeaways for Flume: high-level pipelines and optimization, sort of making it easier to write real-world pipelines versus the confining map shuffle reduce paradigm. All right, so next, Storm. So Storm was really interesting because, so it came about in like 2011-ish. So basically, this guy Nathan Mars was trying to get lower latency results and having a really hard time doing it with Hadoop tools. And so he went in and built this new thing called Storm. He actually wrote a very long blog post on it, which is this one here. It's pretty interesting to read. I recommend it. But anyway, the basic idea was, I want lower latency processing, so we're gonna build this thing that'll let you build up DAGs of processors and just process data in a streaming manner. That was great. The downside was that in order to get this low latency, they sacrificed a lot of stuff that Hadoop had around consistency. And so what you ended up with was this system that really didn't guarantee you correct results like you got with Hadoop. Like up until this sort of stuff started happening, if you ran a data processing tool, you just assumed, if you ran it 3 times, you'll get the same output because why would you want anything else? But in order to get low latency, they started sacrificing some stuff. This actually led to the Lambda architecture, which again, I imagine a lot of you are familiar with. Basic idea being, you want to get low latency results, but you want them to be eventually consistent as well. So you take your big data set, you run it through something like Storm, gives you low latency, but not correct. And then later you also run them through Hadoop. This gives you correct results at a far later time. Somehow you merge them together in the end, and this works out great. Mod the fact that you're running 2 separate systems and maintaining them and merging results. Lambda architecture was begat by this blog post by Nathan, also an interesting read. He framed it as like I'm beating the cap theorem, which was this thing from Eric Brewer that I've never been a huge fan of. On that note, slight aside, if you haven't read Martin Klapman's critique of the cap theorem, I highly recommend this. He has a much more interesting, I think, take on consistency and guarantees and things like that. But segue aside, back to the timeline. So conceived and launched 2011-ish timeframe. His company got acquired by Twitter, so that's how Storm became associated with Twitter. Lambda architecture became very prevalent. Trident was this thing to try to fix some of the consistency stuff in Storm by making a micro-batching system on top of Storm. That didn't work out so well, I don't think. Became an Apache project in 2014. Really interesting development was last year, 2015, Twitter came to us all and said, oh, hey, by the way, so we've been using Storm for a long time, and it turns out we had a really hard time making it run the way we wanted as far as performance and reliability. So we just kind of rewrote the thing as this thing called Heron. And that's been open sourced too now. So you have this other Storm-compatible system called Heron out there. So it'll be interesting to see how that all develops. And also Storm 1.0 came out this year finally. And it has a lot of advancements in it, some out-of-order processing stuff, some windowing stuff. So that sounds very promising. I haven't used it myself yet though. There's a Heron paper if you want to learn more. It's a very interesting read. So the really interesting thing as far as what Storm brought to the table for streaming was that it was really the first system that I think had large impact of providing low latency stream processing. Like it wasn't the first stream processing system ever by any means, but it certainly made a huge impact within the industry. But it came at a cost. Like it came with weak consistency, and it basically brought along the baggage of the Lambda architecture. All right, so next up, Spark. Again, I think you've probably all heard of Spark. And I will similarly with Hadoop, I won't be doing Spark justice here. But the basic idea of Spark is built around this concept of RDDs, or at least it used to be. They're kind of moving on to more advanced stuff, but I haven't updated my slides, so I'll just talk about RDDs. The basic thing with RDDs is, well, at least I always kind of viewed RDDs as like, these are your data sets, whatever. But the really interesting part about RDDs is that they actually store the lineage of how those data sets were created within the pipeline. And so the nice thing is then if you ever lose like a partition or a shard, the RDD knows how that was constructed so that it can go and rebuild it. Some of the other interesting things Spark did, which I'm sure you all know about, are in-memory processing and iterative and ML and all sorts of things that have helped it become as popular as it has. But basically, they had this really nice batch processing system, and they said, well, hey, why don't we do streaming with this? Why don't we just do this a lot, and we'll make this a streaming system? So they built this micro batch system, which basically just runs Spark repeatedly. So you run it once, you get some outputs, and you just keep running it over a continuous data stream, which really is what a lot of folks have been doing with batch systems forever anyway, dealing with continuous data. They've got data coming in all the time. They run a batch job, and they process it. And then after that finishes, they run another one. So that works pretty well. It works great when you are dealing with unbounded data and just doing like element-wise processing, so maybe filtering, like in this case. It works really well if you are windowing by processing time. So when as data arrive, you bundle them up into windows based off of when the stream showed up, and then process it. So it works great for in-order data. It doesn't work so great for out-of-order data because data arrive and you sort of treat them as being within a window, but in reality, you kind of need to shuffle them into the windows that match the event times where they actually happened. And Spark itself had no support for this natively. They're starting to add this in Spark 2.0 and beyond. But at the time at least, that was not really an option. So timeline-wise, came out of Berkeley's AMP lab, what was that, 2009. First Spark paper was in 2010, Spark streaming paper in 2012. Matei's dissertation was in 2014. I've got some sorting benchmark numbers on here as well. And yeah, Spark 2.0 came out recently and looks to be quite interesting. If you're going to read one thing about Spark as far as papers go, I highly recommend Matei's dissertation. It's this massive tome of like everything Spark, and it's really well written. It's full of all sorts of great stuff. Yeah, highly recommend it. So from the perspective of sort of Spark's impact on stream processing, and again, this is vastly understating Spark's overall impact within the industry, but as far as just within stream processing, the really interesting thing they brought to the table was they brought strong consistency to in-order stream processing. Like before this, pretty much all the other systems out there, you didn't have strong consistency. You didn't have correctness, and Spark brought that to the table and really upped the ante, which was awesome. So next, MillWheel. So MillWheel is one of the systems I've worked on for the last 6 years. It's Google's stream processing engine. It was also founded around the time Flume was, when the Seattle office opened. Both Flume and MillWheel were Seattle projects. It was really founded around 4 key motivations. One was the same latency reduction thing that all these other streaming projects were focusing on, wanting to be able to process unbounded data in a natural way. But there were 2 things that the team focused on from the beginning that really shaped the way that the system evolved. One was an absolute requirement of correctness. We were not going to support something that couldn't let you get correct results. and 2 was out-of-order processing. We knew that the nature of distributed data sets was that in a lot of cases, you were not going to be able to get your data in order, but in order to provide correct results, you're going to need to provide tools to deal with that. And so what this meant was that you could take MillWheel and you could build systems that could do this out-of-order processing. So you could do windowing where your data arrive out of order and, say like that green element that's got the white line going down, it showed up between 12 and 13, but it actually happened in 11 and 12, and so we did this time-based shuffle to put it into the right window. Also, because it naturally handled out-of-order unbounded data, you could do things like sessions and do them right. You could do them so that you wouldn't get these arbitrary session boundaries. You could just build up a session and actually output it when it was complete. Sessions are really interesting because they're sort of windows that are based off of the data itself. And I don't have time to go into them in as much detail as they deserve, but so be it. The foundations for all this, there were really 4 things. One was this focus on correctness. You had a system that gave you strong consistency and could give you correct results. 2 was the ability to have persistent state, so you could accumulate state over time. That's necessary for doing things like this time-based shuffles of getting stuff into the right time window. The third one was watermarks, so this notion of completeness. Even though you have out-of-order data, you have a notion of how complete the data is up to a given point in time, and that may be a guarantee or it may be a heuristic estimate. I'll talk more about that in just a couple slides. And then timers, which basically let you say, call me back sometime in the future, either when some time has passed or when you think the data is complete up to a given point in time. And this lets you orchestrate things happening in response to outside signals. So watermarks, quick little deep dive on these. So watermarks basically is a way of describing event time progress. It's a guarantee of some sort that no timestamp earlier than the watermark will be seen again. And if you have perfect knowledge of your input source, you can create a perfect watermark, which is awesome because then you'll have no late data. But oftentimes they have to be heuristic based because oftentimes you can't know everything about your input data. Think mobile devices, like they go online, they go offline. Somebody might go offline for 2 days, then take airplane mode off and upload events from 2 days ago. There's just no way for your system to know that stuff's going to happen. 2 issues with watermarks, they can be too slow. So if they're rightfully holding back the watermark because they know about data, your watermark may lag, but if that's the only thing that's stimulating results in your pipeline, you might not get results as quickly as you would like. They may also be too fast. That's the heuristic-based issue of if their estimations are not accurate enough, they may be moving too quickly and you may get late data. If you want to learn more about watermarks, again, I recommend Slava's talk. The slides are fantastic. We'll get a video up somewhere. You can also check the MillWheel paper. This was at VLDB in 2013. It goes into watermarks quite a bit as well. And then most of the rest of the paper is focusing on strong consistency. Timeline-wise, founded 2007, put on there like when state and timers and watermarks showed up. Zeitgeist, I just mentioned that. I think that was when the Zeitgeist pipeline launched into production. That's the one that's mentioned in the VLDB paper. MapReduce mode is this interesting thing I threw up here. I don't think we've talked about this anywhere else. This was basically, we had a bunch of customers who, they want to deal with unbounded data. They want low-ish latency, but they don't need like single-digit seconds. Like they're kind of okay with 10 minutes of latency or 20 minutes of latency, and they'd rather pay less for that. And so MapReduce mode was essentially replacing our RPC-based shuffle with a MapReduce in the middle of it. So instead of shuffling to the next stage, you would write out to a file, and then once you buffered up enough data, the next stage would then just essentially be a MapReduce reducer and read that data and process it. So it's basically micro-batching integrated into a streaming system. And they could trade off, they could basically choose, do I want the full streaming mode, which is going to be more expensive, or do I want this higher latency but cheaper micro-batch version? So that was kind of cool. Streaming Flume, again, we'll talk in more detail about Cloud Dataflow. That's essentially what streaming Flume looks like. But the main takeaways from MillWheel was strongly consistent out-of-order streaming. Let's see here, how much time do I have? 15. All right. So Cloud Dataflow. So Cloud Dataflow happened in, I want to say 2013. Yeah. So 2013-ish, Google basically decided, hey, we've got this Google Cloud Platform thing. We've been doing this MapReduce and Flume and MillWheel stuff. We should build this into a big product that folks in our cloud platform can use. So we went and built Cloud Dataflow. And Some of the interesting part of Cloud Dataflow is it centers around this what, where, when, and how idiom that we originally developed in streaming Flume. Basically is a way of thinking about data processing and the main questions you need to ask. So, what are you computing? So these are your results. Is it a summation? Are you building histograms or machine learning models? Where in event time? So is this sort of not, you don't care about event times, it's sort of a single global window, or is it, hourly fixed windows, or is it sessions? When in processing time do you materialize your results? Do you wait until you've seen all of your input, or if you have unbounded data, do you wait until you think you've seen all the input for the window, or do you want speculative early results? And what do you do if you have late data? So that's what the when question tries to answer. And then in cases where you do have multiple results, how do refinements of those results relate? Are they disjoint? Do they build upon one another? And so these translated directly into pieces of the API. So the what question is answered by transformations. Those are the P transforms from Flume we talked about earlier. Where is basically windowing. The when question is answered by a combination of watermarks and triggers. So that's basically the two talks Slava and Ken gave yesterday. And then the how is this, what are these different, how do things accumulate over time? Accumulation mode. So there's a VLDB 2015 paper on this that goes into great detail if you're curious. The basic idea is, on a given data set, this system provides you the flexibility to choose a whole suite of different types of outputs that match your use case. So you can do like classic batch processing. You can run a batch job that does fixed windows if you're actually dealing with window data. You can do a streaming job that gives you a single result per window. You can do streaming jobs with early and late data. You can do streaming jobs with retractions if they're implemented, which they're not for us yet. But and then you can do things like sessions, which is a really powerful thing to do. And you can basically just add a line that says, sessions. And the cool thing is that like the code for this, the difference between these is not really that great. And I'm not expecting you to be able to read this, but you can look at the slides later if you want. But basically it allows your code to evolve very cleanly, even though you're making very, very strong changes to the semantics of your pipeline. So by separating these out into these important, distinct questions, you can sort of change the answers to those questions without radically having to rewrite your code, which is really cool. Again, Ken's talk yesterday covered this in detail. If you missed it, those are the slides. Another thing Cloud Dataflow brought to the table was this managed service thing. So you'd write your code, you'd send it to Google, they'd run it through their optimizer, they'd go schedule jobs, they'd bring them up on GCP, launch VMs, et cetera, and all this happened in the cloud. So you don't have to do anything as far as ops go. You just write your code and you kind of watch it run, which is cool. Other things that we try to do in Cloud Dataflow, auto-awesome stuff. So I'd mentioned reduce sub-sharding in the MapReduce section. That was kind of a precursor to this, to liquid sharding. So this is in batch. Like the idea here is dynamic work rebalancing. I'm sure you're all probably familiar with like straggler shards that make things run slow. So Dataflow has this thing called liquid sharding or dynamic work rebalancing, whatever they ended up calling it. But if it detects straggler shards, it automatically rebalances them, and it ends up, because you're basically, your execution time is going to be how far to the right the thing went, right? So by rebalancing dynamically as it runs, it can drastically shrink the runtime of jobs in the presence of stragglers. So anyway, not a whole lot of history here because it's only a couple of years old. Founded, launched, we had our VLDB paper, and then Beam happened, which we'll talk about later, so I'll go into that when we get to that. Main takeaways for Dataflow. Main takeaways for Dataflow. This unified batch and streaming model. So you treat the two as basically the same thing, right? Batch is really a subset of streaming. Anything you can do within the system works in both batch and streaming. You do it by working through these what, where, when, how questions. This way of thinking about your problem, which makes it a lot easier to evolve or adapt it to different situations. And then Cloud Dataflow brings a managed service and auto-awesome features that are really nice. So, Flink. So this is the last one that's not Google that I'm going to talk about. So Flink happened, well, it sort of depends on how you look at it. So Flink is an evolution of a bunch of research that happened at TU Berlin. The first 4 things on there are various papers, NFL, Pact, Iterative, and Stratosphere. So there's a bunch of interesting papers that were in TU Berlin, basically converged on this system called Stratosphere. And then eventually it was renamed Flink and became an Apache project around 2014. So you can sort of argue when Flink actually began. But the really interesting stuff in Flink happened primarily last year was when they started happening. So they added snapshot support, which is really how they baked strong consistency into the system. And so that's when things started to really get interesting for Flink. And then also around that time, they basically adopted the Dataflow model wholesale. So they took all the concepts that we had used for our model in Dataflow and adopted them into Flink. And so they very quickly added very robust support for out-of-order stream processing over the course of the year. And that all was included then in Flink 1.0, which was released earlier this year. I think most of it was actually in Flink 09, but anyway. This is the paper that describes how their snapshot system works. It's pretty interesting. It's definitely a very high performance type of consistency model. The basic idea is that they've got this DAG of processors, right, and it's sending data between them. On the same data channels, they send these checkpoint barriers, and so at any given processor, it knows who all of its upstream nodes are, and it waits for all the checkpoint barriers to come, and when they all arrive, it stops at checkpoints, and then it moves on, and if it then crashes before it gets to the next checkpoint, everything has to roll back to the last checkpoint and replay. So it needs something like Kafka on the front end that lets you replay. But as long as you have that, it's actually a very nice and highly performant system. So interesting read for that paper. So main takeaway then for Flink was that it really was the first truly compelling open source streaming engine for out-of-order processing. So that then leads us to Beam. Let's see, how much time do I have? 8 minutes. So Beam. So Beam happened earlier this year, actually. So it came about in February. And so what is Beam? I actually get this question a lot. So Beam is a few things. So at the core of Beam is that what, where, when, how model for data processing that I talked about. It's this unified streaming and batch model that lets you think about your data processing task in a way that composes well, that is easy to break apart, evolves well, things like that. It's also, number two, it's also a set of SDKs for writing pipelines. So it's concrete manifestations of this model. We started out with Java. We actually have Python, and Python is in the repository. It's not released yet, but it's under development. And there will be others coming as well. And then it's a set of runners for executing pipelines written in Beam on various distributed processing backends. And so we came out of the gate with Apache Flink, thanks to Data Artisans, Apache Spark, thanks to Cloudera, and also, of course, Google Cloud Dataflow support managed service. Because really, the SDKs I talked about in 2, it was basically the SDK from Google Cloud Dataflow that we donated to the Apache Foundation. And so one interesting point with Beam is that even though Beam, we're up to like 0.20 release or something like that, we're working on 0.30. I forget the precise number, but even though it's in early stages, like this is code that's been running, like all Cloud Dataflow customers are essentially running on this, and this is code that we've sort of evolved over the last 13 years at Google. So this is very heavily tested, heavily developed code. This isn't just some new project. I kind of stopped halfway through the runners. There's also a direct runner for testing, but you can also run it, if you don't have massive data right now, but you think you might someday, you can actually run on the direct runner on a single machine. And if you get to the point where you need to scale up, you can switch onto one of the other distributed runners, which is kind of a cool thing. And then we've got 2 other runners that are coming. So Apache Gearpump, the incubating project, that's Intel stream processor. We have basic support for that in the feature branch. It's not rolled into the main repository yet, but it's close. There's an Apache Apex runner in progress. I thought I'd heard rumors of a Storm one, but maybe they're just rumors. It'll happen. So the technical vision for Beam is that we're going to have three folks that we're basically working for here. There's end users who want to write pipelines and transform libraries and a familiar language, Java, Python, etc. There's SDK writers who want to make the Beam model accessible in a new language, so maybe JavaScript or Scala or whatever. And then there's runner writers who they have their own distributed processing engine and they want to make it accessible to anybody who's written a pipeline in Beam. Rough timeline of the project. So we entered incubation in February. Quite a lot of chaos in the beginning because there was all the package renaming, and this was a good chance to make breaking changes. We've kind of entered a phase of API stabilization, and the goal is to, by the end of the year, have stable releases running on multiple runners. One other question that comes up a lot is, well, how do I know what I can do with various runners? So we actually have a capability matrix on the website where you can go and you can see various pieces of the model, and they're sort of broken out by those what, where, when, how questions. So, you know, windowing and triggering and things like that, and the various columns of the various runners, and this will be expanding over time as we add more runners and as runner capabilities increase and things like that. And then lastly, one of the things that I'm really excited about is, you know, becoming an Apache project means that we now have a chance to actually grow this into a real community. Like, so we can work with folks in the community. We already have a lot of folks joining in who aren't just Googlers. I mean, it was founded with a bunch of companies that weren't just Google, but even beyond that. And also it gives us a chance to grow well beyond what we could reasonably fund at Google. So I'm very excited to see what happens here and very glad we were able to make this into an Apache project. So big takeaways for Beam was that it's trying to provide a portable standard APIs for robust out-of-order data processing within the broader open source ecosystem. So in conclusion, because I have 3 minutes or something. So the main points that I claimed were important, at least for the thesis I'm presenting here. You know, MapReduce brought about scalability and simplicity. Hadoop really brought big data, this open source ecosystem thing. Flume with the idea of pipelines and optimization, so you can write clear, maintainable code that's still highly performant. Storm bringing low latency processing to the masses. Spark bringing strong consistency for in-order processing. MillWheel sort of bringing the basics of out-of-order processing, the low-level nuts and bolts you need for that. Cloud Dataflow with its unified batch and streaming model. And then Flink really bringing out-of-order processing to the open source world. And then Beam providing portability in this standardization layer. That's kind of the whole history that has led us here. And then my final thesis, I told you this was a Beam pitch. You know, in my opinion, the future of streaming and batch data processing is Apache Beam. Nobody wants to be rewriting their pipelines. You know, we all want a robust and sophisticated standard, so we can write our pipelines once, and you know, as engines evolve, maybe we want to move somewhere else. Just think of what SQL has done. So that's basically my thesis for this talk. Thank you for coming. Any questions? No questions. All right. No, seriously, questions? All right, brave man in the middle.
Well, you kind of mentioned SQL, so I know, like, for example, Spark and Spark Streaming have an interface that's essentially a SQL interface with like data frames. So how does that kind of go together with the Beam model of expressing pipelines?
So we'd love to see a SQL DSL for Beam. As of yet, there is no SQL dialect that adequately encompasses everything we need for robust out-of-order stream processing. Julian Hyde and Apache Calcite have some proposals for some things that get us in that direction. I've been talking to Julian, some other folks on our team have been talking, so we're working in that direction. What I'd like to see happen is that we define basically the core things that you would need within SQL to do out-of-order stream processing, and at that point it would be viable to have something on top of Beam. So there's work happening there, and other projects like, Flink is using Calcite to do some amount of stream processing, but they don't have anything out of order in it yet, but yeah. Hope to see it happen. In blue.
What's left before it leaves incubation and becomes 1.0 type of offering?
We're pretty close. Do you have any thoughts on that, Ken?
I would separate 1.0 from leaving incubation.
Ken would separate 1.0 from leaving incubation. If you want more details, come talk to Ken and I afterwards. We're getting close, though. Yes, sir.
How does integrate Flink and Spark machine learning libraries?
Currently, there is no machine learning support in Beam. If you would like to contribute there, we would love to hear your thoughts. It's a wide open field. In the back. So I think the question is, how does Beam relate to the Dataflow SDK? Beam will be Dataflow SDK 2.0. There will be no, Dataflow SDK is 1.0, and it is already essentially in maintenance mode. And once Beam is out, that's going to become Dataflow SDK 2.0. We will not develop them separately. Everything will be in Beam. Yes, they will be one and the same. Like, Beam is the Dataflow SDK. Yes?
So I have some exposure to Apache NiFi. I don't know if this is related to that. Apache NiFi.
Okay.
Also doing processing, workflow.
Yeah. I don't know a whole ton about NiFi. I imagine you could build a NiFi runner for Beam. I imagine like NiFi has some kind of cool like graphical design stuff, doesn't it? I imagine you could build a graphical design layer for Beam, which would also be very cool. Again, if anybody wants to contribute that sort of stuff, we'd love to see it.
How do you handle the semantics difference between different platforms?
So the question is, how do you handle the semantic differences between different platforms? So runners can, basically runners, so what happens is you write a Beam pipeline. It essentially gets compiled down into this sort of intermediate description of what the pipeline looks like, this kind of interchange format, and runners can look at that and say, well, like you use this trigger, I don't support this trigger, and basically throw an exception and say, I'm sorry, you tried to use a feature that we don't support. Does that get at what you're asking?
Yeah, that's why you have the table.
Exactly, so you can know ahead of time. I mean, the other thing, there are things like you reasonably could run a pipeline that is not exactly once, doesn't support exactly once processing, it supports at least once mode. You could run that and you wouldn't necessarily throw an exception, but you wouldn't be getting the same thing that you would get from running on a pipeline that supports exactly once processing. Well, you sort of have to know up front, like it's a runner thing, right? Like if you run it on an old version of Storm that doesn't support strong consistency, that's just what you're gonna get, So, and once we have more runners that have more variety of semantics like that, we'll be adding that to the capability matrix too. Anything else? Sorry, say that again? Question is whether it's Beam's responsibility to control access to the underlying data. I think that's more or less, well, is your question like ACLs, or is your question like who implements the actual reading from Kafka? That kind of a thing. I said, is your question like how is ACLing handled, or is your question like, say for Kafka, do we have a Beam implementation of Kafka, or does Beam just sort of thunk down to like Flink's implementation or whatever? So it's a security question you're asking? We don't have anything related to security or ACLs at this point in time, so that for now it falls onto the runner. There's certainly no reason we couldn't bake that into the API, it's just not something that exists at the moment. I don't have an answer for that. We'd have to look at it. It may very well be in certain cases, but any other questions? Oh, over here.
Start building the ecosystem for things like in Dataflow you have the big table, big query. So at some point they will be merged. Sorry, the Dataflow will be merged with without the ecosystem.
Well, the idea with the ecosystem is really to be able to interface with everything that exists out there. So you should be able to interface on, if you're on Google Cloud Platform, you should be able to interface with Cloud Bigtable or BigQuery, but this isn't just about GCP at this point, right? So really anything within the ecosystem, you should be able to use Kafka, you should be able to introduce, interface with HDFS or anything within the broader open source ecosystem that you want to use, you should be able to interface with Beam with that. So I'm not sure if that answers your question, but there's no real plans to yeah, I mean, BigQuery is basically a SQL API, so there's not a whole lot to port there. Cloud Bigtable already uses the HDFS API, so in that sense, they've kind of already just committed to what is already the open source standard. So I don't think there's anything else for them to do either. Or H-based, I should say, sorry. Yes? So is the question, can two pipelines, can you interoperate between different runners in different pipelines?
Yes.
So you can run, so a given pipeline, you can write it once and you can run it on any runner you want. So if that's the question, you can do that. As far as talking together, like you'd have to use any sort of interconnect that you would use in any normal circumstance. So you could use Kafka, right, to talk from a Flink pipeline running on, a Beam pipeline running on Flink to a Beam pipeline running on Spark. There's no, you can't do like half of a pipeline on Flink and the other half on Spark, if that's the question.
The resource management, right? So does it, runners take care of the resource management?
Yeah, currently it's all runner. So the question was resource management. Currently it's all runner specific. So like whatever runner you're running on, what, if you're running on Yarn or whatever, whatever setup you're using, it's sort of all related to that. You just use Beam as the way to describe your pipeline, and then you launch it on the normal, whatever normal setup you have. So it's a very tricky thing to deal with. I mean, the ideal is that you have this thing called retractions. So if you read either Streaming 102 or the Dataflow model paper, it goes into details about those. But the basic idea is, if you've emitted 2 partial sessions and they later get joined into one big session, what you really want to do is emit retractions saying, I'd said that there are these 2 small ones, get rid of those, and now there's this new one that replaces them. If you don't have that, it's a lot trickier to deal with if you're doing multiple firings per session. Yeah, I was totally wrong. Just get rid of that thing. Here's the new thing. Yeah. Anything else? Nope. Well, thank you all for coming.